Now we're going to use calculus to analyze and graph the rational function y equals 2x cubed plus x squared plus 1 over x squared plus 1. Looking at the function, we can see that the domain is all real numbers. We can also see that the y-intercept is 0, 1. As far as an x-intercept is concerned, we're going to take the numerator, 2x cubed plus x squared plus 1, and set it equal to 0 because the numerator of a fraction is the only thing that can make it equal to 0. This doesn't factor. I'm going to use synthetic division. My spidey sense tells me that if I use -1 in the synthetic division, then everything will work out just fine. 2, 1, 0, and 1 are our coefficients. And bring down the 2, multiply and add a few times. And we have that x plus 1 times 2x squared minus x plus 1 is equal to 0. Looking at the quadratic factor, if we look at just the discriminant, b squared minus 4ac is equal to 1 minus 8. That's negative. And so that factor is not going to give us any real zeros for the function. Therefore, our x-intercept is going to be -1, 0. As far as any horizontal asymptote, there isn't one. The degree of the numerator is greater than the degree of the denominator. And so if we were to find the limit as x approaches 0 of y, we would say, well, that's infinity. But whenever the degree of the numerator is larger than the degree of the denominator, our path is to use long division. For us here, that means we've got 2x cubed plus x squared plus 0x plus 1 divided by x squared plus 1. I'll spare you the details. And when I'm using long division in a situation like this, I stop before I get to any remainder. What we have here is an asymptote that looks like y equals 2x plus 1. That I'm going to abbreviate as SA. And here we're looking at what's called a slant or oblique asymptote. And that's what we're going to get out of the function itself. Let's turn to the derivative. I've put the function in front of us again. What I would like for you to do is go ahead and find the first derivative and look at intervals of increasing and decreasing, and then come back when you're done. All right, hopefully you got that y prime is 2x to the fourth plus 6x squared over the quantity of x squared plus 1 squared, giving us a critical number of x equals 0. And because our exponents are even all over the place, this derivative is never negative. So we are increasing from -infinity to 0, and then from 0 to infinity. And if my graph goes increasing and then 0 and then increasing, that means we have what I call a wiggle. And I'll go ahead and put that in quotes because I made that up. We're going to look at the second derivative together because of something that happens with rational functions. I got ahead of myself. I need to identify u and v. So u is 2x to the fourth plus 6x squared. V is x squared plus 1, the quantity squared. U prime is going to give me 8x cubed plus 12x. And then v prime, I'm going to use the chain rule. So 2 times the quantity of x squared plus 1 times 2x. That's coming out from the chain rule. So u prime v is going to give me 8x cubed plus 12x times x squared plus 1, the quantity squared. And then uv prime is going to give me 2x to the fourth plus 6x squared. I'm going to multiply 2 by 2x to get times 4x, and then leave x squared plus 1 factored. You'll see why in just a minute. And then our denominator is going to be x squared plus 1 squared, so to the fourth power. Now, the thing that happens with second derivatives for rational functions that I alluded to just a minute ago is you'll notice the base of v, in this case x squared plus 1, is present in all terms in the numerator and it's in the denominator. Therefore, one factor of that is going to divide out. Look for that when you're finding the second derivative of a rational function. It's much better than smashing everything together and then trying to factor it out later. At this point, I'd like you to just challenge yourself to go ahead and clean this up and get the second derivative in a nice tidy expression. And I'll just wait a beat so you can pause it. You can see my work here, and if you need to pause it to get the details. I'm going to factor out a negative from the numerator of my result, and I'm going to end up with y double prime equals negative 4x times the quantity of x squared minus 3 over x squared plus 1, the quantity cubed. So values that I'm going to mark on the x-axis for y double prime are going to be 0 and plus or minus the square root of 3. Using test points in these defined intervals, I like to do things like if it's to the left of negative square root of 3, since square root of 3 is like 1.7 something, I'm going to pick like negative 5 or negative 10, something that makes it obvious for me. That gives me a positive factor here, a positive factor here. The denominator is always positive, so I don't have to worry about that. And I see that positive, and so concave up. Between negative square root of 3 and 0, x equals negative 1 looks good. Continuing on like this, we see concavity alternates positive to negative, which means we have some inflection points at x equals 0 and plus or minus the square root of 3. We need to find y coordinates associated with these x coordinates. Of course, we already found that at 0 the function value is 1. At 3 we get 3 square root of 3 over 2 plus 1. Excuse me, that's at square root of 3. And at negative square root of 3 we get negative 3 square root of 3 over 2 plus 1. So we can say our inflection points are 0, 1, square root of 3, 3 square root of 3 over 2 plus 1. I know it's a lot to write. And negative square root of 3, negative 3 square root of 3 over 2 minus 1. Okay. I want to go ahead and summarize all this, but I'm going to ask you to do it first. We dealt with y, we dealt with y prime, and we dealt with y double prime. I'd like for you to gather together all the stuff that we've done, and then see if you can sketch the graph and then come back when you're done. So my summary is that for the function y, our domain is all real numbers. X-intercept is negative 1, 0. Y-intercept is 0, 1. Slant asymptote, y equals 2x plus 1. I'll come back to this note in a minute. For y prime, we got a critical number of x equals 0, increasing on the interval from negative infinity to 0, and also from 0 to infinity. I know that means we have a wiggle at x equals 0, no local extrema. For y double prime, concave up on the interval from negative infinity to negative 3, and also from 0, concave up on the interval from negative infinity to negative square root of 3, and then also from 0 to the square root of 3, concave down on the interval from negative square root of 3, 0 to square root of 3, also square root of 3 infinity. Make that a little union there. Whoops. And we have inflection points at 0, or that are 0, 1, negative square root of 3, comma, negative 3 root 3 over 2 plus 1, and square root of 3, comma, 3 root 3 plus 2 over 1, 3 root 3 over 2 plus 1. Folks, I don't want you to write down like plus or minus a, comma, plus or minus b in this case. That actually implies 4 different points. A, B, negative A, B, A, negative B, and negative A, negative B. I know it's tempting to want to write down plus or minus for these, but we only have 2 points. We don't have 4, so it doesn't work in this case. Approximations for the x coordinates of the inflection points are plus or minus 1.73. And then for the y coordinates, the negative one is about negative 1.6, and the positive one is about 3.6. So we have some points to plot and a slant asymptote, some inflection points, and that's what I have here. Here's my slant asymptote, y equals 2x plus 1, and the various points that we saw. And our graph is to be concave up, and then concave down, and then concave up, and then concave down, with a horizontal tangent, a brief horizontal tangent at x equals 0. And so here we're going to be concave up. Whenever you're below an asymptote, or the graph is below an asymptote, your function is going to be concave. Did I say up? This is concave down. Yes, concave down there. And if I'm above an asymptote, then the graph will be concave up. And I think I kind of oversold that a little bit. So here we're concave up. So again, if your function is above a vertical, horizontal or slant asymptote, it'll be concave up. If it's below a horizontal or slant asymptote, it'll be concave down. You can kind of see why that is, right? If this were to bend to be concave up, it would eventually cross and then get away from the asymptote. Now we're concave up here for x, between 0 and square root of 3. And then we have that wiggle and we go concave down. And the point here really is that all of this information should come together and agree with each other. The concavity with the critical number tells me I have that wiggle. And this, I don't like how that is down there. So I'm going to bring that. Yeah, I don't like that either. Ooh, I like that much better. This should be asymptotic here. And it should be asymptotic here. Hopefully you can see the value of using calculus and derivatives to find out the details for a graph like this.